Okay, what we're going to talk about now is a big topic in inferential statistics. It's our first big move where we talk about how the sample truly represents the population. And we're going to talk about what we call confidence intervals around the estimate. And we are only going to deal with two estimates at this time. We're going to build confidence intervals around x bar and confidence intervals around p hat. What we're going to say is we have so much percentage of confidence such that we can say x bar represents mu, and therefore our sample represents the population. And you may think in your brain that is a big jump for just one parameter of the population to be estimated by the statistic, but remember that we talked a lot about the standard deviation of that statistic, and so the standard deviation also plays a role. So we use a couple parameters to estimate and make our conclusions about the population. The proportion is the same thing. It's going to be talking about p, and we want p hat. It's going to represent the population proportion, and therefore we can make conclusions about the population based on our sample. Now the problem is we can never be 100% confident. And the reason why we can't be 100% confident is because we're talking about a sample. If we were 100% confidence, 100% confidence would imply we used all info or data from the population. And truly, that's kind of impossible, depending upon the populations that you're talking about. So we always say we are so since we are using a sample, we can say we are what we call 1 minus alpha percent confident, which you just kind of deal with the fact that I threw an alpha out there, and it'll all make sense when I draw some pictures. Hopefully, that's the plan, that it makes sense. Okay, so remember that our estimate from the previous lectures is x bar or p hat, and both follow a normal distribution. So because of that, when we build these distributions, again around mu, and they're based around mu because the mu of x bar is mu, and same with the proportion. The middle of this is just p because mu of x bar equals mu, and p hat equals p based on the central limit theorem. So because the central limit theorem, which we talked about a couple lectures ago, makes this conclusion for us, we can use the normal distribution, and what we're going to do is, if we're using the mean or we're using the proportion, it doesn't matter. This inside here is the 1 minus alpha level of confidence, and therefore because confidence intervals are typically two-sided, though we will do with some one-sided, then the tails are going to be alpha over 2. And here, again, alpha over 2 and alpha over 2. So let me put some numbers in so you know what that kind of means. So if I want to make a 95% confidence interval on mu based on x bar, in here will be the 95%. So that's the 1 minus alpha where that comes into play. Well, alpha over 2, so if 1 minus alpha equals 0.95, then alpha must equal 0.05. Therefore, alpha over 2 equals 0.025. So it means the area of the tails of a 95% confidence interval each have 2.5% of the probability of results, which from a confidence interval perspective, it means that 95% of the time, or 95% of the samples that we're going to pull from our population, even though we just pull one of them, 95% of them should fall within that 1 minus alpha range, and the other 5% fall out here, just meaning they're bunk samples. You didn't get the overall population that you were looking for. You found samples that just truly are not representative. And so because they don't represent, we can't be 100% sure. We're only 95% sure. We could also be 99% sure and 80% sure, though that's not very sure enough. We need to be a little more sure than 80%. If we do in red here, this 99% confidence interval, let's say on P, and it's going to be based on P hat, well, then in here we have the 0.99. Therefore, if 1 minus alpha is 0.99, which 99% confidence is pretty good confidence, then alpha equals 0.01, and therefore this equals 0.005, and this is 0.005. So that's the idea behind the confidence. And what our job is going to be is to find these numbers on this normal distribution, like right here and right here, in order for us to be able to bind our estimates x bar and p hat. So that's what we're going to do for the confidence intervals. The issue with finding those estimates is we have to use the empirical rule within the normal distribution to find those estimates. So the way we do that is, we know that if we go, if we look in our z-tables, which you have done on several examples, if you use the z-tables, and the z-tables are always centered around 0 with a standard deviation of 1, if you want to mark off 95% of the probability, you know that the z-score is 1.96 and negative 1.96, or about 2, right? The empirical rule says 2. The actual integration tells us 1.96 and negative 1.96. If we want to do %, those values are, they go a little bit further out. They are 2.58 and negative 2.58. So they go a little bit further out, not quite to 3, but a little bit halfway. So those are the points, and what we're going to do is we transfer the standard normal curve back into the curve that talks about our data. So the way we transfer it back to the data is we use the z transformation. And so we have some formulas. A 95% confidence interval on mu is given by x bar plus or minus 1.96 times the standard deviation, which is sigma over the square root of n. And if we want to do and if that's like, what, did I just make that up? No, I did not make that up, right? So I solved that equation, making it equal to 0.95. I back solved it from before. If I want a 99% confidence interval on mu, it's x bar plus or minus 2.58 times sigma over the square root of n. And I can also do, you can be less confident. Sometimes you'll see reports in reading where they have a lower alpha level, like a alpha level of 0.1. It means that they aren't quite sure that their sample was that good, but they're going to report on it anyways. And that one has the z-score corresponding to 1.64 over sigma square root n. Again, these numbers, 1.96, 2.54, and 1.64, are coming from the z-tables, measuring how much probability is between two numbers. 95% is between negative and positive 1.96, 99% is between negative 2.58 and 2.58, and 90% between plus or minus 1.64. We can keep going here and talk about the same thing. If we want we'll go from least to greatest here. A 90% confidence interval on p, the population proportion, is you take p hat and you add and subtract 1.64. And this time sigma, though, in this case, is always that square root of p hat 1 minus p hat over n. A 95% confidence interval on p is p hat plus or minus 1.96. And a 99% confidence interval. I'm sure at this point you see the pattern that's happening. We base it around the p hat statistic, the point estimate, and then it's 2.58 times that standard deviation, which is p hat 1 minus p hat over n. So those are the formulas for the confidence intervals that we will be generating. We also will generate them using software, because that's more typical how it's done by people who are researching today, is they just have their data and they want to build confidence intervals on the population they claim the data comes from. And then typically they're testing if some value they found falls within that confidence interval. Sometimes it doesn't fall on that confidence interval and they need to do their research a little more in depth, or it does and they can publish a paper. So that's the formulas for it. What I want to do next is start with an example. And so we're going to do an example of a mean. So I'm going to switch pages here. Okay. Well, let me go back and do a clarification, though, which I talked about with the central limit theorem, but let me just make sure that's real clear before we move on. In all the above cases, x bar and p hat, this sample size better be greater than or equal to 30. And that's actually not that hard to do in a sample to get it bigger than 30. However, sometimes you just don't have enough to sample and it has to be smaller. If n is less than or equal to 30, we build different confidence intervals, which we'll talk about in the next lecture. So beware of that. So everything in these examples that I'm going to do are always going to have kind of a bigger sample size to guarantee the power of the test. Otherwise, we can't use these z-scores. We have to use some other kind of score because they're not truly normally distributed. Okay, so let me write the example down. Example. The average sorry, I need to erase that. I lost my train of thought for a second. The textile industry claims that the standard deviation of the breaking strength of yarn is 2 psi. What that means is pounds per square inch. So it's just a measurement of how textiles are kind of measured in the industrial engineering process. So if we take a random sample of 98 pieces of yarn and find we're going to do it of 50 pieces of yarn, and we find that the average breaking strength is 98 psi. The directions say find a 95% confidence interval on the true breaking strength. Okay, so we have to set up our confidence interval, and we do that by first labeling everything we need to label, right? So the first thing is we need to know what our sample size is. Our sample in this case is 50. We need to know what X bar is. X bar comes from that sample, and it's 98. And then that first sentence tells me that sigma, the standard deviation from the population, is 2. So because of that, I have everything I need. I know that a 95% confidence interval is set up in such a way that I take X bar and I add and subtract to it about 2 standard deviations, and those standard deviations, because I'm talking about X bar, is sigma over the square root of n. So I'm going to start to build it here, fill in all the blanks, so I get 98 plus or minus 1.96 times 2 over the square root of 50. So now you just have to be really careful that you're doing your order of operations right in your calculations. So the first thing I'm going to do is I'm going to divide 2 by the square root of 50. So I'm doing that right now. 2 divided uh, 50 square root. Okay. Divided by 2 equals, and then I'm going to flip it. Okay. So this is 98 plus or minus 1.96 times, and if you do that, you should get 0.2828. Okay, then you're going to multiply that by 1.96. Okay, and this is 98 plus or minus 0.5544. Now it should just be noted here that this indicates then we really have two calculations. We have the 98 minus the 0.5544, and we have the 98 plus 0.5544. The 98 minus is 97.4456, and the plus is 98.5544. So giving you time to do those calculations. So what that means is the 95% confidence interval ranges between 97.4456 and 98.5544. And that's the answer for the 95% confidence interval. The graph that's kind of like working alongside this in the background says that this confidence interval is based around 98. And then it gets bounded here by 98.5544 and 97.4456. And so what that means is we know that 95% of the samples from that population produce averages between the 97.4456 and 98.5544. So we know that our mean is bounded between those. You can also say that you are, and this is what most textbooks say, is that you are 95% confident that that mu, the population breaking strength, is between 97.4456 and 98.5544. So what another way to say that is 5%. You have 5% error, and that means that you could have had a bunk sample, but based on this, your mean should fall in here, talking about the main population. And that's a lot of power to say based on one sample, right? One sample of 50 produced a confidence interval so that you can say the population is bounded between two numbers based on that because my sample was a strong sample, and the central limit theorem says that we can do an inference on our population based on our sample, as long as the sample was good. That's why we talk so much about simple random samples. The next thing I'm going to do is I'm going to build a confidence interval based on a proportion and then ask a couple more questions about it. So I want to do that example here. Okay. It's that semiconductor example that I worked on before to talk about p-hat. Okay, so here's the example. A semiconductor. So we're going to find a 99% confidence interval for the true proportion of defective controllers. Okay, so we're going to start the solution the same way we did before. The first thing we got to know is what's that sample size. That sample size, it says, is a simple random sample of 200, so n is 200. And we know that our point estimate, p hat, for defective is 4 out of 200. That would then indicate that q hat, or the complement of that, is 196 out of 200. So we kind of need to know all that information. And the 99% confidence interval would be p hat plus or minus 2.58 times the square root of 4 over 200 times 196 over 200 over 200, right? If we fill in all the blanks from the formula. So what we're going to do is we're going to go through and do those calculations. I always like you to do the calculations with me so that you kind of know where the numbers are coming from, that I'm not making them up as I go through this process. So the first thing I want to do is probably we need to get everything into a little bit more of a decimal example, because that I think is easier. P hat is equal to 0.02, right? If you do the division right here, you get 0.02. So 0.02 plus or minus 2.58 times the square root of, we now know that's 0.02. We know that the complement of it must be 0.98, right? And we're going to multiply those two things. And then we're going to divide by 200. So that leads me to have 0.02 plus or minus 2.58, and now I'm going to work inside those parentheses. So I have 0.02 times 0.98, and I'm going to divide that by 200, which I think in my calculator I just divided it by 20. So let me make sure I put enough zeros in. So 0.02 times 0.98 equals, divided by 200 equals, that looks a little better. I'm going to take the square root of that number, and then I'm going to multiply it by 2.58. And I get, let me divide that by, this is 0.0098. It's really 0.0099, right? Okay, so I'm going to keep going there. And I'm going to go 0.02 plus or minus. Now I'm going to take that and multiply it by 2.58, and I get 0.0255. And then again, I'm going to break it into my bounds, my confidence interval. So I have 0.02 minus that, and then I have 0.02 plus that. So I keep going, and notice what happens here. I actually get gotta clear, so 0.02 minus 0.0255 equals. So this side is actually negative 0.0055, which in this example is going to just bound it by 0, because you can't have negative semiconductors. But the point is that very few are going to be defective because they have such an awesome manufacturing process. And this is 0.0455. So this confidence interval that we just created, we're going to round that to 0 just because it makes sense in terms of what we're talking about. Sometimes you can have negative numbers in a confidence interval. And so this means that we are 99% sure or confident that the true proportion of defective controllers is between 0% and 4.5%. Again, I just took these numbers here and changed them to percent. You'll see that happen all the time when you actually read papers of research, is that they don't typically write about it in terms of the raw decimal numbers. They usually convert it to a percentage just for the ease of the person reading it. So again, that's a confidence interval for a proportion. In all of these examples, that sample size is bigger than 30. The next lecture will be what happens if that sample size is smaller than that.